What if I told you that the very ground we walk on holds secrets far deeper and more mysterious than we ever imagined? Picture this: beneath bustling cities, quiet forests, and vast oceans lies another world entirely. A world of darkness, silence, and impossible complexity. A world of underground labyrinths. These are not just simple caves or tunnels. They are immense, interwoven networks, carved over millions of years, twisting and turning through the earth in ways that defy easy explanation. For centuries, these hidden realms have captivated explorers and scientists alike. How did they form? What forces could possibly create such intricate and expansive structures deep below the surface? We're about to dive into one of the most compelling and surprisingly overlooked theories, one that connects these subterranean wonders to one of Earth's most powerful and invisible forces: its magnetic field. You see, Earth's magnetic field is so much more than just what makes a compass point north. It's a dynamic, living shield generated by the churning of molten iron in our planet's core that protects us from solar radiation and cosmic rays. But this shield isn't constant. Throughout history, it has faltered, weakened, and at times completely collapsed in events known as geomagnetic reversals, where the north and south magnetic poles swap places. These weren't quiet, unnoticed events. They were episodes of planetary instability that left their mark across the globe. And it's within these periods of magnetic chaos that some scientists believe something extraordinary happened underground. Increased radiation, shifts in climate, and intensified geological activity may have accelerated the carving of these vast labyrinths, sculpting hidden worlds in the dark. In this video, we're going to journey through time and rock to uncover how the collapse of Earth's magnetic field might be the missing piece in this ancient puzzle. We'll explore everything from the science of paleomagnetism, reading the memory locked inside stones, to the breathtaking beauty of cave systems like Mammoth Cave and volcanic tubes in Iceland. We'll look at how water, tectonics, and even human history intertwine with this grand geological narrative. This isn't just a story about rocks and magnetism. It's a story about how our planet works in ways we're only beginning to understand. So come with me. Let's venture into the depths, decode the clues left behind, and see the hidden architecture of our world in a completely new light. Think of it as a colossal, invisible force field enveloping our planet, born from the furious churning of superheated liquid iron thousands of miles beneath our feet in Earth's outer core. This immense dynamo, a spinning ocean of molten metal, generates an electrical current that in turn creates our global magnetic shield. It's this shield that acts as our first and most vital line of defense against the relentless onslaught from the sun, a constant stream of charged particles and radiation known as the solar wind. Without this protective barrier, our atmosphere would be slowly but surely eroded away, stripped by these cosmic forces, leaving the surface exposed and barren, much like the landscape of Mars. But this magnetic field is anything but a static, unchanging dome. It's a dynamic, almost breathing entity constantly in flux. Its strength ebbs and flows, and its magnetic poles are not fixed points. They wander across the Arctic and Antarctic landscapes, sometimes dozens of miles in a single year. The history of this movement is literally written in stone. When volcanic lava cools, tiny magnetic minerals within the rock lock into place, aligning with the magnetic field's direction at that exact moment in time, creating a permanent record for scientists to later decode. Sediments settling at the bottom of ancient oceans do the same, preserving a layered history of the field's behavior. These geological archives reveal a startling truth. our magnetic shield has undergone dramatic transformations throughout Earth's history. It has weakened to a fraction of its current strength, surged to become more powerful, and most astonishingly, it has completely flipped its polarity on numerous occasions. These events, called geomagnetic reversals, see the north and south magnetic poles trade places. This isn't a quick, simple switch. It's a protracted and chaotic process that can span centuries or even millennia. During this extended transition, the magnetic field doesn't just weaken, it can become a tangled, multi-poled mess, drastically reducing its ability to protect the planet. This leaves Earth vulnerable to increased levels of solar and cosmic radiation, which can have profound effects, potentially disrupting power grids, altering satellite orbits, and even influencing climate patterns by affecting cloud formation and atmospheric chemistry. It is within these extended periods of magnetic instability and turmoil that we begin to see the possibility for other, more tangible changes to our planet, changes that could reach deep into the crust itself and play a crucial role in sculpting the hidden, labyrinthine worlds beneath our feet. So what exactly happens during one of these geomagnetic reversals? It's not a simple, clean flip of a switch. Instead, imagine it as a prolonged period of planetary identity crisis, a slow-motion cosmic drama where the Earth's magnetic field becomes unstable and disorganized. The process begins with a significant weakening of the field's overall intensity. During the most chaotic phases, the strength can plummet to as little as 10% of its normal power. This isn't a uniform dimming either. It's more like the field begins to fray at the edges, developing multiple, competing magnetic poles that pop up in strange places across the globe. For a time, you might theoretically have several north poles, one near Brazil, another off the coast of Florida, while the traditional poles start a slow, wandering migration across the planet's surface. This erratic dance of the poles can last for centuries, sometimes even millennia, creating a magnetic landscape that is utterly chaotic compared to the stable, two-pole dipole we rely on today. The entire shield becomes a tangled, complex web, offering far less protection from the harsh environment of space. We know this isn't just theoretical because Earth's geological record is filled with the evidence. The most recent full-blown reversal is known as the Matayama reversal, which was completed around 780,000 years ago. But a more recent and intensely studied event is the Labyrinths excursion, which occurred approximately 41,000 years ago. This wasn't a full reversal, but rather a dramatic excursion, a significant weakening and temporary flip of the field that lasted for about 1,500 years before it snapped back to its original orientation. The signature of the Labyrinths event is preserved in volcanic rock from France, deep-sea sediments, and even ice cores from Greenland and Antarctica. These ice cores show a spike in radioactive isotopes like beryllium-10 during that period. Because a weaker magnetic field allows more cosmic rays to reach the atmosphere where they create these isotopes, the ice acts as a direct historical record of the magnetic field's collapse. Unlocking this ancient history is the work of a scientific discipline called paleomagnetism. It functions like a forensic science for Earth's magnetic past. Here's how it works. When certain minerals rich in iron, like magnetite, are heated to a very high temperature, say in a flowing lava, their internal magnetic particles act like tiny compass needles floating freely. The moment that lava cools past a specific point, called the Curie temperature, those microscopic compass needles freeze perfectly in place, permanently aligned with the direction and intensity of the magnetic field at that exact moment in geological time. The same process happens much more slowly at the bottom of oceans or lakes. as magnetic particles in settling sediments gently orient themselves with the field before being locked into place as the sediment turns to rock. By carefully drilling out core samples of these ancient rocks and sediments from around the world, scientists can take them back to the lab. Using incredibly sensitive instruments called magnetometers, they can measure the precise magnetic direction frozen within the sample. By then using other dating techniques like radiometric dating for volcanic rocks, they can build a precise timeline of when the field was pointing where and how strong it was. This painstaking work has allowed us to map out hundreds of these reversal events throughout Earth's deep history, revealing a rhythm that is both unpredictable and fundamental to our planet's nature. This foundational instability sets the stage for everything we'll explore next, priming us to understand how such profound electromagnetic chaos could potentially reverberate through the solid rock beneath us and trigger the geological processes that carve out hidden worlds. Now, let's turn our attention from the invisible forces above to the breathtaking, tangible wonders below, the staggering underground labyrinths that weave through the crust of our planet. These are not merely holes in the ground, they are nature's most intricate and patient architectural projects, carved over spans of time that are almost impossible for the human mind to comprehend. They form through a fascinating combination of relentless physical and chemical processes. In places like the limestone bedrock beneath Kentucky, slightly acidic rainwater percolates down through the soil, slowly dissolving the soluble rock over millions of years, gradually enlarging tiny fractures into massive caverns, silent rivers, and towering domes. In other regions, like the volcanic slopes of Hawaii, labyrinths are born from fire, not water. Here, rivers of molten lava flow across the landscape. The outer surface cools and solidifies into a rocky shell, while the still liquid interior continues to drain away, leaving behind long, hollow tunnels known as lava tubes. Tectonic forces also play a massive role, as the immense pressures of shifting continental plates can fracture entire sections of crust, creating vast networks of faults and fissures that water then exploits and expands into complex, multi-level mazes. To truly grasp the scale and artistry of these formations, we can look at some of the world's most famous examples. The Mammoth cave system in the United States is a titan among labyrinths, a sprawling, epic network with over 400 miles of explored passageways, and geologists believe there could be hundreds more miles waiting to be discovered. Wandering its depths is like exploring a subterranean city, with avenues, rooms, and galleries that leave explorers in a state of perpetual awe. On the other side of the world, in New Zealand, the Waitomo glowworm caves offer a different kind of magic. Here, a silent boat ride on an underground river reveals a ceiling glittering with the bioluminescent light of thousands of tiny creatures, turning a geological wonder into a starry night sky hidden deep within the earth. And then there are the immense volcanic tubes like Kazumura Cave in Hawaii, which plunges for over 40 miles and descends more than 3,600 feet beneath the island's surface, a stark reminder of the raw power that once flowed there. For centuries, the accepted explanation for these wonders has centered on these visible, measurable processes: water-dissolving rock, lava-building tubes, and the Earth's crust cracking under pressure. But what if that's not the entire story? The sheer complexity, the global distribution, and the timing of accelerated growth phases in some of these labyrinths have led a number of scientists to ponder a more profound, more universal catalyst. Could there be a hidden trigger, a planetary scale event that acts as a great accelerator for these geological processes? This is where our previous exploration of Earth's magnetic turmoil comes sharply back into focus. The hypothesis is as groundbreaking as it is fascinating. Perhaps the periods of extreme instability during geomagnetic reversals, with their associated spikes in radiation, climate disruption, and potential for increased tectonic stress provided the unique environmental conditions necessary to dramatically speed up the carving and formation of these subterranean masterpieces. It's a theory that connects the celestial dance of our planet's core to the very ground beneath our feet, suggesting that the chaos above may have been the silent architect of the beauty below. So if a faltering magnetic field can affect the skies and the climate, what might it be doing to the very ground beneath us? This is where the theory moves from the atmospheric to the deeply geological, proposing a direct and physical link between magnetic chaos and the very forces that carve our planet's subterranean labyrinths. The chain of events begins with that dramatic increase in solar and cosmic radiation. While much of this energy interacts with the atmosphere, a significant portion penetrates the Earth's surface. This isn't science fiction, it's a measurable phenomenon. This influx of energy can cause a subtle but widespread heating of the upper crust. Now, on its own, this heating might be minor, but in a planet already brimming with internal heat and pressure, it can act as a critical trigger. Think of it like preheating an oven before you bake. It creates the right conditions for things to start happening more easily. This external energy input can potentially influence the immense engine of our planet, the mantle. The mantle is not liquid lava, but a seething, viscous solid rock that flows over millions of years, driving the movement of tectonic plates above it. Changes in heat distribution and pressure at the base of the crust, possibly influenced by this increased radiation, could subtly alter the convection currents within the mantle. Even a minor shift in this immense system can have colossal consequences at the surface. One of the most direct potential consequences is a surge in volcanic activity. Magma chambers, which are vast reservoirs of molten rock trapped below the surface, might become destabilized. The additional energy could lower the melting point of rocks or provide the final push needed for magma to force its way through weaknesses in the crust. There is intriguing evidence for this. Studies of volcanic rock sequences, particularly along mid-ocean ridges where new crust is born, appear to show increased eruption rates during periods known for magnetic reversals. It's as if the planet itself becomes more volcanically restless when its magnetic shield is down, and where there is increased volcanic activity, the formation of one specific type of labyrinth explodes lava tubes. During these periods of heightened eruption, more frequent and voluminous lava flows would naturally create more of these hollow, tunnel-like structures. But the effects aren't limited to fire, they extend to the shattering force of earthquakes. The same tectonic stresses that build up and are released along fault lines could be amplified. The added thermal stress from a warmer crust can make rocks more brittle and prone to fracture. Furthermore, the potential changes in mantle convection could apply new, direct pressure on the tectonic plates, increasing the rate of collisions, subduction, and slippage. This would lead to a period of more frequent and potentially more powerful seismic events. Every major earthquake does more than just shake the surface. It grinds rock against rock deep underground, pulverizing stone and opening up vast new networks of fractures and faults. These newly created fractures are the blueprints for future labyrinths, the primary pathways that water will later exploit to begin its slow, dissolving work. This brings us to the master sculptor itself, water. The impact on groundwater could be profound. Increased seismic activity violently shakes the underground aquifers and water tables, effectively pumping water through these systems with immense force, accelerating the dissolution of soluble rocks like limestone. Furthermore, the climatic shifts associated with magnetic reversals, potentially toward wetter or icier conditions, would deliver more water to the system overall. More rainfall means more acidic water seeping into the ground, and more meltwater from glaciers can create powerful underground streams that act like liquid sandblasters, scouring out cave passages at a vastly increased rate. This creates a powerful feedback loop. Tectonic activity creates the fractures, and climate-driven water then rushes in to widen them into caves. Some of the most compelling supporting evidence for this entire theory comes from precisely dated cave formations. In various cave systems around the world, scientists have analyzed stalagmites and flowstones, and their growth layers show distinct, rapid growth phases. Incredibly, some of these accelerated growth spurts coincide remarkably well with the known timelines of past geomagnetic excursions. This suggests that during these unstable periods, something likely a combination of increased water flow and available space from new fractures dramatically sped up the cave-forming process. It paints a picture of a planet in geological overdrive, where the collapse of an invisible shield in space triggers a cascade of events that literally reshapes the world below. To truly grasp how a planetary event like a magnetic reversal could physically reshape the world below us, we need a tangible, real-world example, a place where the scale is so immense, the evidence so layered, that the theory moves from abstract to astonishingly plausible. There is no better case study than the Mammoth cave system in Kentucky. This isn't just a cave, it's a subterranean continent, a hidden world woven through the bedrock. With over 400 miles of explored passages mapped so far, and geologists confident hundreds more miles await discovery, it holds the undisputed title of the longest known cave system on Earth. Wandering its depths is a humbling experience. You're not just in a tunnel, you're in a vast, silent cathedral of stone, with avenues that branch into grand rotundas and canyons that plunge into absolute darkness, all carved over millions of years. Its primary architect is something deceptively simple: water. Rainwater, slightly acidic from absorbing carbon dioxide in the soil, slowly percolates down through the vast limestone shelf that underpins this region. This weak acid tirelessly dissolves the calcium carbonate that holds the rock together, first seeking out the tiniest hairline fractures, then patiently, grain by grain, enlarging them into the colossal passages we see today. But the story of Mammoth Cave's formation is not one of slow, constant, and predictable growth. The geological evidence preserved in its walls tells a story of fits and starts, of long periods of quiet development punctuated by intense, explosive bursts of creation. It's within these bursts that we find our potential connection to Earth's magnetic turmoil. Scientists can read this history by studying the cave's speleothems, the stalagmites, stalactites, and flowstones that decorate its chambers. These formations grow incrementally, layer by layer, as mineral-rich water drips from the ceiling or flows over surfaces. By using advanced radiometric dating techniques, particularly uranium-thorium dating, researchers can analyze these layers with incredible precision, building a detailed timeline of when the cave was most actively growing. What some of this research has revealed is nothing short of remarkable. There appear to be distinct periods spread across hundreds of thousands of years where the growth of these formations accelerated dramatically. These growth spurts indicate a massive increase in the amount of water flowing through the cave system, water that was not just dripping but gushing, actively dissolving and enlarging passages at a ferocious rate. The pivotal question is, what could possibly trigger such a sudden and massive hydrological change deep underground? This is where the timeline becomes the key piece of evidence. When researchers compared these periods of accelerated cave development to the established paleomagnetic record of Earth's history, they found a compelling correlation. Several of these intense growth phases in Mammoth Cave align closely with the dates of known geomagnetic reversals and excursions, such as the Brun-Smatayama reversal around 780,000 years ago and the much younger Lashump excursion. This alignment is the cornerstone of the hypothesis. The mechanism is thought to be a cascade effect originating from the magnetic chaos above. A significantly weakened magnetic field would have allowed a substantially greater amount of solar radiation to reach the Earth's surface. This influx of energy could have acted as a powerful climate disruptor, potentially altering atmospheric circulation patterns and supercharging the hydrologic cycle. The result in this region could have been a shift to a much wetter climate with increased and more intense rainfall. More rain means more acidic water seeping into the ground, feeding the underground rivers that are the lifeblood of cave formation. Furthermore, the increased seismic activity potentially linked to magnetic instability could have violently shaken the entire region. Major earthquakes would have fractured the limestone caprock on a massive scale, creating a brand new network of pathways for water to exploit. It's the difference between a slow trickle through a clogged pipe and a torrent unleashed through a freshly shattered landscape. The cave system wouldn't just be growing, it would be undergoing a period of rapid, violent renovation. The evidence locked in the stalagmites of Mammoth Cave suggests that during these times of magnetic collapse, the quiet, patient work of water was supercharged into a frenzy of dissolution, sculpting miles of new passageways in a geological heartbeat. This isn't just a theory about rocks and magnetism, it's a story written in stone and water, a permanent record of how chaos in the sky above can leave an indelible mark on the world below. While the patient work of water carves labyrinths in stone, fire forges its own kind of hidden world with a speed and violence that is almost unimaginable. These are the volcanic lava tubes, nature's brutal and breathtaking answer to the underground maze. Their formation is a dramatic, high-stakes process. Picture a river of incandescent molten rock, temperatures soaring beyond 2,000 degrees Fahrenheit, rushing down the slopes of a volcano like a blazing avalanche. The outer surface of this flow, exposed to the cooler air, begins to crust over and solidify into a dark, rocky shell. But beneath this hardening skin, the heart of the flow remains a furious, liquid torrent. It continues to race downhill, eventually draining away completely and leaving behind a long, hollow, tunnel-like cave, a perfect cast of the lava river's path. These tubes can be mere inches wide or become monumental subterranean highways large enough to drive a bus through, stretching for dozens of miles through the volcanic landscape. They are the raw, igneous cousins to the water-sculpted caves, and they offer a completely different but equally compelling piece of the magnetic puzzle. The connection here hinges on a fundamental question. Could the instability of Earth's magnetic field directly influence the very fires of the planet's interior? Some geophysicists are exploring a fascinating and controversial possibility. The theory suggests that the significant increase in solar and cosmic radiation that penetrates to the surface during a magnetic reversal might do more than just heat the upper crust. It could potentially transmit energy and disturbance much deeper, into the very upper layers of the mantle where magma is born. The mantle is a seething, plastic solid, but it's incredibly sensitive to changes in heat and pressure. An external energy influx, even if relatively small, could act as a trigger, subtly altering convection currents, reducing the pressure on superheated rock, or lowering the melting point of mantle material. This could lead to the formation of larger magma chambers or make existing chambers more unstable and prone to eruption. It's the geological equivalent of turning up the heat under an already simmering pot. Eventually, it's going to boil over. This isn't just theoretical speculation. The volcanic rock record itself seems to hold clues. In places like Iceland, a global hotspot for both volcanic activity and the study of paleomagnetism, there are intriguing correlations. Vast fields of ancient lava flows, which undoubtedly once contained extensive tube systems now collapsed or buried, have been radiometrically dated. The ages of these major eruptive sequences sometimes cluster around the known timelines of past geomagnetic reversals. Similarly, in the Pacific Northwest of the United States, the immense lava flows that created the Columbia River Basalt Group, a landscape literally built from frozen floods of lava, show evidence of eruptive pulses. While dating such a massive event is complex, some studies suggest its timing may not be entirely divorced from periods of magnetic instability. It's a pattern that hints at a planet whose internal fire burns brighter during its moments of electromagnetic chaos. To walk through one of these tubes today is to step into a frozen moment of that planetary fury. Explorers, their headlamps cutting beams through an absolute darkness that has persisted for centuries, navigate a world of surreal textures. The walls are often glassy smooth where the molten rock once flowed, or they are draped in fantastic ripples and waves frozen in solid stone. The ceilings are frequently studded with hardened lava drips known as lavasicles, and the floors can be a chaotic jumble of collapsed rock from the ceiling above. It is a stark, powerful, and incredibly fragile environment, and within the very rock that surrounds them lies a hidden diary waiting to be read. When that lava initially cooled and solidified, the iron-rich minerals within it, primarily magnetite, did something extraordinary. As the temperature of the rock dropped below 580 degrees Celsius, the Curie point, these minerals became magnetic. In that instant, they locked into their structure the exact direction and intensity of Earth's magnetic field at that precise moment in time. This means that every chunk of basalt in a lava tube is a silent, stony witness to the magnetic conditions the day it was born. By carefully sampling these rocks and analyzing their paleomagnetic signature, scientists can determine if the tube was formed during a period of stable, strong magnetism, or if it was born amidst the turmoil of a reversal or excursion. A lava tube whose rock shows a clear, strong magnetic signal pointing to today's north likely formed during a quiet period, but a tube whose rock records a weak, scattered, or completely reversed field. That tube is a direct artifact of magnetic chaos, a tunnel forged in fire during one of Earth's most dramatic identity crises. It becomes not just a geological feature, but a time-stamped piece of evidence, directly linking the collapse of a planetary shield to a surge of volcanic creativity deep underground. But while fire carves with a dramatic, singular fury, water is the patient artist of the underground, working with a slow, persistent grace that ultimately creates the most extensive and intricate labyrinths on Earth. Its primary canvas is a type of landscape known as karst, a world defined by soluble bedrock. Imagine rainfall not as a simple shower, but as a weak acid. As each drop filters through the soil, it absorbs carbon dioxide, transforming into a mild carbonic acid. This is the secret weapon. When this slightly acidic water encounters soluble rocks like limestone, which is primarily composed of calcium carbonate, or the even softer gypsum, a silent chemical war begins. The acid reacts with the rock, slowly dissolving it molecule by molecule. This isn't a violent process, it's an insidious one. The water seeks out the tiniest weaknesses, a hairline fracture, a minuscule joint between crystal grains, and begins to enlarge it. Over centuries, that hairline fracture becomes a fissure. Over millennia, the fissure becomes a tunnel. Over eons, an entire network of caverns, sinkholes, and underground rivers can form, creating a Swiss cheese-like architecture hidden deep beneath a seemingly solid surface. This process, however, is almost never constant. The flow of water, the lifeblood of karst formation, is entirely at the mercy of the climate above. A long period of drought can slow cave growth to a near standstill, while an era of exceptional rainfall can turn a slow trickle into a raging subterranean torrent, accelerating dissolution exponentially. This is where the collapse of Earth's magnetic field re-enters the story as a potential global climate disruptor. The mechanism is both elegant and powerful. A weakened magnetic field allows a significantly greater influx of high-energy cosmic rays to penetrate our atmosphere. These cosmic rays don't just light up the sky with auroras, they act as seeds for cloud formation. When they collide with molecules in the atmosphere, they can ionize them, providing a surface for water vapor to condense around. This leads to increased cloud cover and can fundamentally alter global precipitation patterns. The result could be a planet-wide shift toward more extreme and erratic weather. Regions might experience prolonged, intense deluges, while the accumulation of ice in polar regions could also be affected, leading to periods of rapid glacial melt. Both scenarios deliver a massive surge of water to the landscape. Now, picture this cascade effect on a karst region like the Great Limestone Plateaus of Kentucky or the Yucatan Peninsula. A period of magnetic instability triggers a climatic shift toward a much wetter regime. The skies open up, delivering rainfall not in gentle showers but in torrential, ground-saturating downpours. This isn't just more water, it's water with a mission. All that additional precipitation, already slightly acidic, now has immense hydraulic force behind it. It doesn't just seep gently into the ground. It pours into sinkholes, floods into cave entrances, and forces its way under pressure through every available pore and fracture in the rock. This supercharged hydrological cycle acts like a turbocharger for cave formation. The water's dissolving power is multiplied, and its physical force scours and washes away the dissolved rock debris at a vastly increased rate, preventing passages from becoming clogged and allowing the system to expand rapidly. It's the difference between a sculptor patiently sanding a piece of wood and using a high-pressure sandblaster. The most compelling evidence for this theory isn't found in the vast, open caverns, but in the delicate, jewelry-like formations that adorn them, speleothems. Stalactites, stalagmites, and flowstones are not just decorations, they are the climate archives of the underground world. They grow incrementally, layer by microscopic layer, as mineral-rich water drips from the cave ceiling or flows over its walls. Each layer's thickness and chemical composition is a direct record of the amount and quality of water that was moving through the cave system at that specific time. By using precise uranium-thorium dating techniques, scientists can analyze these layers and assign exact ages to them, building a detailed, high-resolution timeline of a cave's hydrological history. This is where the connection snaps into startling focus. In studies of speleothems from various caves across Europe and Asia, researchers have identified distinct, rapid growth phases periods where the formations grew exceptionally quickly, indicating a massive surge in water flow through the cave. Incredibly, the dates of these growth spurts show a remarkable correlation with the known timings of past geomagnetic excursions, like the Lachamp event. It's as if the speleothems themselves are recording the moment the planet's shield flickered. The water, responding to a climate supercharged by cosmic rays, began to flow faster and in greater volume, dumping more calcite and causing the formations to grow at an explosive rate. This transforms these beautiful cave formations from mere geological curiosities into silent, stone witnesses chronometers that recorded the precise moment when chaos in the magnetic heavens above triggered a flood in the hidden worlds below, dramatically accelerating the sculpting of Earth's deepest labyrinths. While the patient work of water and the fiery force of volcanoes are powerful sculptors, They both require a canvas to work upon a pre-existing network of weaknesses in the planet's solid crust. This is where the immense world-shaping power of tectonics takes center stage. The Earth's outer shell is not a single, unbroken sphere. It's a dynamic jigsaw puzzle of massive plates that are constantly, imperceptibly shifting. They collide with unimaginable force, they grind past one another, and they slowly pull apart. This relentless motion doesn't just build mountains and carve ocean basins at the surface. It sends powerful shock waves of stress deep into the bedrock, fracturing it on a continental scale. These fractures, the faults, joints, and fissures created by this tectonic pressure, are the absolute fundamental blueprints for every major underground labyrinth. They are the primary pathways, the initial cracks that water will later exploit and lava will later flow through. Without this tectonic pre-processing, these vast networks simply could not form. Now consider the added variable of a geomagnetic reversal. We've established that a significantly weakened field allows a surge of solar and cosmic energy to bathe the planet. This energy doesn't just stop at the surface, it penetrates the upper layers of the crust, depositing heat. While this heating effect is subtle in the grand scheme of the Earth's immense internal furnace, it can be critically important as a trigger mechanism. Rock, under the colossal pressure of being buried for miles, is already under immense strain. Adding even a small amount of thermal energy can be the proverbial straw that breaks the camel's back. The heat causes the rock to expand minutely, increasing the strain on already stressed fault lines. It can make brittle rocks even more brittle, lowering the threshold of stress needed for them to suddenly snap. This concept, known as Coulomb failure stress, is a key principle in seismology. It suggests that a small, external perturbation can provide the final nudge that initiates a major earthquake on a fault that was already primed to rupture. The geological record offers tantalizing hints that this isn't just a modern theory. Paleoseismology, the study of ancient earthquakes by examining offset layers in sediment trenches, and the analysis of marine sediment cores have both revealed patterns. In certain regions, there appears to be evidence for clusters of significant seismic activity that coincide broadly with the timelines of known magnetic reversals. For instance, studies of rapidly deposited sediment layers in the Pacific Ocean, which are often triggered by major earthquakes and landslides, seem to show increased frequency during periods like the Matayama Brun's reversal. It paints a picture of a planet that doesn't just get a magnetic headache during these events, it gets the geological shakes. To see this process in action, we can look at some of the most tectonically active landscapes on Earth. The East African Rift Valley is a spectacular example, a place where the continent is literally tearing itself apart. As the tectonic plates diverge, they create a massive, yawning network of parallel faults and fractures. Groundwater immediately drains into these freshly opened wounds in the landscape, and in the regions underlain by limestone, this has led to the rapid development of extensive cave systems. The caves here are often linear and fault-controlled. Their layout's a direct map of the tectonic stress field that created them. Similarly, in the complex subduction zones like those found in Indonesia or the Caribbean, the intense compression and shearing of rock creates a dense, chaotic web of fractures. On islands like Puerto Rico or Java, some of the most impressive cave networks are found running directly along these major fault lines, their passages tracing the angles of the tectonic forces that shattered the rock eons ago. The impact of a major seismic event on cave formation is immediate and profound. An earthquake does not just create a single new crack, it violently rattles the entire bedrock fabric. It can pulverize rock, creating vast fields of broken rubble underground. It can forcefully slam existing faults together, grinding the rock along their surfaces into a fine, easily erodible powder known as fault gouge. Most importantly, it can suddenly and dramatically increase the permeability of the rock mass. Before a quake, water might be confined to a few narrow channels. Afterward, it has a brand new, sprawling highway system of interconnected fractures to flow through. This massively accelerates the entire cave-forming process. Water with renewed dissolving power can now access fresh rock over a much wider area, and the physical force of the water is amplified as it's forced through these new constrictions. A single major tectonic event can effectively take a millennia-long project of slow, gradual cave development and kick it into overdrive, creating miles of new potential passageways in a geological instant. This intricate dance between the slow, grinding forces of plate tectonics and the potential catalyst of magnetic instability reveals a planet where the deepest, most hidden architectures are shaped by a conversation between the chaos in the heavens above and the unyielding pressures from the furnace below. So how do we possibly know what Earth's magnetic field was doing hundreds of thousands or even millions of years ago? We can't go back in time with a compass, but we have something just as powerful, the planet's own memory, locked away inside the very rocks beneath our feet. The key to unlocking this ancient diary is a fascinating scientific discipline known as paleomagnetism. Think of it as forensic detective work on a planetary scale. It all hinges on a simple, beautiful property of certain iron-rich minerals like magnetite and hematite. These minerals are essentially tiny, natural compasses. When they are heated to a very high temperature, such as in a bubbling lava flow or a deep-sea volcanic vent, their internal magnetic particles become unlocked, free to spin and move like needles floating in a liquid. In that superheated state, they are completely responsive to the prevailing magnetic field. Then, as the rock cools past a specific critical temperature known as the Curie point, around 580 degrees Celsius for magnetite, something magical happens. Those microscopic compass needles suddenly freeze perfectly in place, becoming a permanent, unchangeable record of the magnetic field's exact direction and intensity at that precise moment the rock solidified. A very similar process happens far more slowly at the bottom of lakes and oceans. As fine sediments rich in these magnetic minerals gently settle through the water column, the tiny particles have time to orient themselves like countless minuscule magnets, aligning with Earth's magnetic field before they come to rest on the bottom. Over immense spans of time, these layers of sediment are buried and compressed, slowly turning into solid rock and forever trapping that magnetic snapshot within their structure. This gives scientists two primary ways to read the planetary record: through the fiery, instant capture of igneous rocks and the slow, patient accumulation of sedimentary layers. The actual work of reading this stony memory is incredibly meticulous. Researchers venture out into the field, often to ancient lava flows or exposed sedimentary cliff faces, armed with a special tool called a portable drill. This isn't a wood drill. It's a precision instrument that uses diamond-tipped bits and circulating water to extract pristine core samples of rock without generating any heat that could scramble their magnetic memory. Each core is carefully oriented, noting its exact compass direction and angle of tilt before it's ever removed, ensuring the original position is preserved. These precious samples are then taken back to a laboratory that is a temple to precision, often housed in a specially designed building isolated from the vibrations of traffic and, most importantly, shielded from Earth's own modern magnetic field. Inside, scientists use unbelievably sensitive devices called magnetometers to measure the faint, fossilized magnetic signal held within each sample. But knowing the magnetic direction is only half the story. The other critical piece is knowing when that signal was recorded. This is where paleomagnetism joins forces with the science of geochronology. For a lava flow that cooled instantly, scientists can use radiometric dating techniques. One of the most common for volcanic rock is argon-argon dating, which measures the radioactive decay of potassium into argon within crystals to determine an extremely precise age. For sedimentary rocks which form continuously, other methods are used, like analyzing the microscopic fossil remains of creatures that lived for specific, knowable periods in Earth's history. By combining the magnetic data with these precise dates from samples collected from all over the world, scientists have been able to construct a detailed timeline of Earth's magnetic history, a chart known as the geomagnetic polarity timescale. This timeline is our planet's biography, revealing not just the dates of the full reversals, but also the shorter-lived wobbles and excursions like the Labyrinths event. It shows us that the field's behavior is not a steady metronome but a complex, unpredictable rhythm of stability and chaos. To make this abstract concept tangible, imagine each rock sample is a single page from a diary written in a unique, invisible ink that only becomes visible under the special light of scientific inquiry. Each page has a date and an entry describing the state of the magnetic world on that day. By gathering thousands of these pages from every corner of the globe, we can assemble the entire story. This powerful chronological framework is the essential Rosetta Stone that allows us to do something extraordinary. Compare the timing of magnetic reversals with the timing of geological events. We can now look at the precise age of a cave formation, a major volcanic eruption, or a layer of earthquake-shattered rock and ask a direct question. Did this happen during a period of magnetic calm, or was it born from the planetary chaos of a collapsing field? Paleomagnetism provides the when, giving us the foundational timeline against which the epic story of the underground labyrinths can finally be read. But the story doesn't end with the rocks that form the cave itself. The very same magnetic minerals that record Earth's history in volcanic basalt and ocean sediment also find their way into the heart of these subterranean labyrinths, creating what might be the most precise and detailed geological archives on the planet. As water flows through the soil and rock above a cave, it doesn't just carry dissolved limestone. It also picks up tiny, heavy particles of iron-rich minerals like magnetite and hematite. These minuscule grains, often finer than sand, are washed into the cave through drips and streams, eventually settling out to form layers of soft, muddy sediment on the cave floor. Even more remarkably, they can be incorporated directly into the speleothems themselves, as each drop of mineral-laden water hangs from a cave ceiling before falling. It leaves behind a tiny trace of calcite, slowly building a stalactite. Trapped within that calcite are infinitesimal amounts of these magnetic minerals, perfectly preserved within the growing crystal structure. This transforms a cave formation from a simple climate recorder into a dual-purpose time capsule. The layers of a stalagmite still tell us about rainfall and temperature through their thickness and chemistry, but they now also hold a separate, parallel record, a continuous, high-fidelity tape of Earth's magnetic field throughout its entire growth. The process of locking in this signal is a fascinating echo of what happens in lava, but at a far cooler and more gradual pace. As the magnetic particles are deposited in the sediment or embedded in the calcite, they are free to move. In the loose, water-saturated mud, they can slowly orient themselves like countless tiny compass needles, aligning with the prevailing magnetic field before they are finally locked in place as the sediment dries or is cemented by later mineral deposits. Within a stalagmite, the particles are fixed instantly as the calcite hardens around them, capturing a snapshot of the field's direction and intensity with every single drip of water. Reading this magnetic diary requires a level of precision that borders on the surgical. scientists don't just break open a stalagmite that would scramble its delicate internal record. Instead, they use a specialized hollow drill bit to extract a core directly up through the center of the formation, much like a tree core sample. This pristine cylinder, which can represent hundreds of thousands of years of growth, is then taken to a magnetically shielded laboratory. There, researchers use incredibly sensitive instruments to measure the faint magnetic signal from each individual layer. By combining this magnetic data with the incredibly precise dates obtained from uranium-thorium dating of the same calcite layers, they can construct a year-by-year, and sometimes even season-by-season, history of the magnetic field's behavior. The results from this cutting-edge research have been nothing short of revolutionary. In several landmark studies, scientists analyzing stalagmites from caves in China, North America, and Europe have identified clear, unmistakable magnetic signals within the calcite that point directly to known periods of instability. They've found layers that show a sudden, dramatic weakening of the magnetic field strength, and others that show the magnetic direction beginning to wander erratically, exactly matching the timeline of excursions like the Lachamp event. This is the smoking gun, direct physical proof that the chaos of a magnetic reversal was not just an atmospheric or climatic event, but a phenomenon that left its mark deep within the silent, dark chambers of the world's caves. The most profound implication of this discovery is the powerful two-way street it reveals. It suggests that these underground labyrinths are not merely passive victims of magnetic chaos, sculpted by the climatic and tectonic upheavals it may have triggered. They are also active historians, diligently recording the very event that might have accelerated their own creation. A growth spurt in a stalagmite caused by a surge of water from a magnetically triggered climate shift will, in its very layers, also preserve the magnetic signature of that same triggering event. The cause and the effect are recorded together in the same beautiful, layered stone structure. This turns each suitable cave formation into a Rosetta Stone for planetary change, allowing us to directly correlate a period of intense underground construction with the specific cosmic conditions that may have made it possible, offering a truly unified field theory written in stone, water, and magnetism. This cascade of cosmic energy doesn't just stop at the surface. It fundamentally reshapes the very engine of our planet's climate, turning the sky into a powerful intermediary between magnetic chaos and the world below. When Earth's protective shield weakens, the atmosphere is bombarded by a significantly greater number of high-energy cosmic rays. These aren't just stray particles, they act like tiny, incredibly efficient catalysts. As they slam into molecules in our upper atmosphere, they ionize them, effectively providing a solid surface around which water vapor can condense. This process, known as cosmic ray seeding, can lead to a widespread increase in cloud formation. More clouds don't just mean more shade, they act as a powerful thermostat and a precipitation machine, dramatically altering global weather patterns. The entire hydrologic cycle can be thrown into overdrive, with some regions experiencing prolonged, torrential downpours while others might shift unexpectedly toward extreme cold, as changes in atmospheric circulation patterns could usher in new ice ages. This isn't a minor shift in the weather, it's a fundamental rewiring of the global climate system, all triggered by the collapse of an invisible magnetic field thousands of miles beneath our feet. We can see the profound evidence of this connection preserved in some of the most pristine natural archives on Earth. Ancient ice cores drilled from the massive glaciers of Greenland and Antarctica. These cores are like time machines, capturing tiny bubbles of the ancient atmosphere and layers of snowfall that have accumulated over hundreds of thousands of years. Within that ice, scientists can measure the concentration of specific isotopes, like beryllium-10 and carbon-14. These isotopes are created when cosmic rays strike atoms in the atmosphere, so their levels act as a direct proxy for how many cosmic rays were getting through. When researchers analyze the timeline of these isotopes, they find unmistakable, dramatic spikes that align perfectly with the known dates of geomagnetic reversals and excursions. For instance, ice core data from the period of the Labyrinths excursion, around 41,000 years ago, shows a colossal surge in beryllium-10, a clear signal that Earth's defenses were down and the cosmic ray flux was intense. But the story doesn't end there. Locked within those same ice layers are other clues, traces of dust, changes in the chemistry of the ice itself, that tell us what the climate was doing at that exact same time. The correlation is startling. Periods of high cosmic rays often align with evidence of significant climatic upheaval, including rapid cooling events and major shifts in precipitation patterns. Now, let's bring this global phenomenon down to the level of a single raindrop falling on a limestone plateau. A climate supercharged by cosmic rays could lead to a much wetter regime in certain parts of the world. Instead of gentle showers, the region might be subjected to monsoon-like intensity for centuries on end. Every one of those raindrops is slightly acidic, and now they are falling in relentless, ground-soaking deluges. This massive surge in precipitation doesn't just run off into rivers, it floods into the ground, supercharging the underground water table. The aquifers become pressurized, and water is forced with immense hydraulic power through every tiny crack and fissure in the bedrock. This isn't just dissolution, it's aggressive, high-volume erosion. The slightly acidic water attacks the limestone with vastly increased force, dissolving it away and physically scouring the passages clean of debris, allowing the cave system to expand at a breakneck pace. It's the difference between a sculptor patiently working with a fine file and switching to a high-powered sandblaster. The entire process of labyrinth creation is put on fast forward. Simultaneously, the same climatic disruption could trigger the opposite effect in higher latitudes, a surge in glaciation. As atmospheric patterns shift colder, wetter conditions could lead to the rapid growth of continental ice sheets. These glaciers are not static blocks of ice. They are colossal, slow-moving rivers of ice that act like planetary bulldozers. Their incredible weight grinds and scours the landscape beneath them, but their impact isn't only on the surface. The immense pressure of a miles-thick ice sheet can actually fracture the bedrock far below, creating new weaknesses. Furthermore, as a glacier advances, its base often contains meltwater flowing under tremendous pressure. This subglacial water is forced into any available fracture where it can freeze. When water freezes, it expands, exerting enough force to literally pry rocks apart in a process called frost shattering. This can open up extensive new fracture networks deep within the crust. Then, when the climate eventually shifts again and the glacier retreats, it leaves behind a landscape that has been pre-processed, crushed, fractured, and riddled with new pathways. Meltwater from the retreating ice then pours into this freshly shattered landscape, immediately beginning the work of dissolving and carving out a new generation of subterranean passages. The glacier itself, in its relentless advance and retreat, can even carve caves directly, scraping out tunnels and chambers at its base or where meltwater flows under the ice. So whether the magnetic crash brings a deluge of rain or an advance of ice, the outcome is the same: a dramatic acceleration in the excavation of the underground world, linking the chaos of the cosmos directly to the sculpting of our deepest labyrinths. Long before modern science sought to explain the world through geology and physics, our ancestors looked upon the same landscapes and wove stories to make sense of the mysterious and the terrifying. They gazed at gaping holes in the earth, at mountains that rumbled and shook, and they populated these liminal spaces with gods, monsters, and spirits. It is no coincidence that some of humanity's most enduring and widespread myths center on the concept of the underground labyrinth. These stories, passed down through generations, are far more than simple fables. They may be the earliest, most intuitive human records of living through periods of profound planetary change, times when the very ground seemed alive and unstable, perhaps during those very episodes of geomagnetic chaos we've been exploring. Consider the most famous labyrinth of them all, the Cretan labyrinth from Greek mythology. This was no mere maze. It was a terrifying, inescapable prison built by the master craftsman Daedalus to contain the Minotaur, a monstrous half-man, half-bull that demanded a regular sacrifice of human flesh. The myth is a story of profound darkness, confinement, and a monster that could never see the light of day. But what if this tale has a geological heart? The island of Crete is seismically active, sitting near the convergent boundary of the African and Eurasian tectonic plates. It is a land riddled with natural caves and gorges. A period of intense seismic activity, potentially triggered or amplified by a weakened magnetic field, could have caused the sudden appearance of a new, vast, and terrifying cave system, or the dramatic collapse of land that created a deep, sinkhole-like pit. For a Bronze Age society, witnessing the Earth literally open up to reveal a dark, twisting network of unknown depth would have been an event of apocalyptic proportions. It's not a huge leap to imagine that such a tangible, frightening phenomenon would require a story to explain it. A story of a monstrous birth and a labyrinthine prison constructed by the gods themselves. This pattern of linking the subterranean to the supernatural is a global phenomenon, not confined to the Mediterranean. Across the Atlantic, many Native American tribes hold deep traditions of spirit caves and underground worlds. For the Hopi people of the American Southwest, their origin story tells of emerging into this world from a previous, subterranean existence through a place called the Sipapu, a small hole in the Grand Canyon considered a sacred portal. The region they inhabit, the Colorado Plateau, is one of the most spectacular karst landscapes in the world, home to countless caves and vast underground drainage systems. Similarly, the Lakota Sioux tell of a race of subterranean beings who created the labyrinthine wind caves of South Dakota, considering them a sacred site of emergence and creation. These aren't stories of fear, but of deep spiritual connection to the earth. A period of magnetic instability, bringing increased rainfall and flooding, could have caused water to surge through these dry cave systems with thunderous force, or opened new entrances through collapses, making these hidden worlds suddenly and dramatically known to the people living above them. Such a revelation would naturally be interpreted not as geology, but as a divine event, the opening of a gateway to another world. The potential connection becomes even more compelling when we look at the timelines. While precise dating of oral traditions is incredibly difficult, archaeologists can date human occupation of significant cave sites. There is evidence of human activity in caves across Europe and Asia that dates back tens of thousands of years. Some of this evidence, found in layers of sediment, coincides broadly with the timeline of the Lachump excursion and other periods of magnetic instability. Imagine a tribe seeking shelter in a cave during a violent storm, only to feel the ground tremble with an earthquake, a quake potentially made more likely by the tectonic stress of the era. They might witness sections of the cave wall crack and collapse, revealing previously unknown chambers twisting away into absolute darkness. Above them, the aurora borealis, supercharged by solar winds hitting the weakened magnetic field, could be dancing in the sky with an intensity never seen before. In the face of such awesome, simultaneous celestial and terrestrial chaos, the human mind seeks a narrative, The story that emerges of gods battling underground, of the earth giving birth to a monster, or of a spirit doorway opening, is a perfectly rational attempt to explain the inexplicable. Our ancestors were brilliant observers. They may not have understood the science of geomagnetic reversals, but they absolutely could have connected the dots between a frenzied sky, a shaking ground, and the sudden revelation of a labyrinth beneath their feet. Their myths, therefore, are not just fantasy. They are a form of paleo-science, a cultural memory encoded in story that points directly to real, cataclysmic events in Earth's history, preserving the awe and terror of living through a moment when the planet itself seemed to lose its balance. For centuries, exploring these underground labyrinths meant relying on the flickering light of a lantern, a length of string to find your way back, and the sheer, daring intuition of a caver squeezing through a passage barely wider than their body. It was a world of shadows and guesswork, where the true scale and connection of these networks remained shrouded in impenetrable darkness. But today, we are no longer limited by the beam of a headlamp. We have begun to illuminate the entire subterranean world at once, thanks to a revolutionary suite of technologies that are fundamentally rewriting the rules of exploration. This isn't just an upgrade, it's a complete paradigm shift, launching us into a veritable golden age of discovery where the deepest secrets of the planet are being revealed not by a single explorer, but by the silent, precise work of lasers, radar, and algorithms. At the forefront of this revolution is LiDAR, which stands for light detection and ranging. Imagine replacing your flashlight with millions of tiny, precisely aimed laser pulses every second. This is how LiDAR works, whether it's mounted on an aircraft flying over a jungle canopy or on a tripod deep within a cave. Each laser pulse shoots out, hits a surface, be it a tree branch, the ground, or a cave wall, and reflects back to a sensor. By meticulously measuring the time it takes for each pulse to return, a computer can build an exquisitely detailed three-dimensional map of the entire environment. In cave exploration, this technology is nothing short of miraculous. Terrestrial LiDAR scanners are now carried underground, where they can digitally capture vast chambers and twisting passages with centimeter-level accuracy in a matter of hours, creating a perfect, permanent digital replica. This allows scientists to measure volumes, analyze erosion patterns, and see connections between passages that would be impossible to perceive with the human eye. But its power doesn't stop at the cave entrance. Airborne LiDAR has an almost magical ability to see through vegetation. When flown over a karst landscape dense with forest, the laser pulses can penetrate the leafy canopy and map the actual shape of the ground beneath. This has led to the stunning discovery of countless previously unknown sinkholes, cave entrances, and even the faint surface expressions of massive underground voids, guiding explorers directly to the next great discovery without a single foot having to set foot in the wilderness. While LiDAR maps the surface and what's already visible, other technologies act as planetary-scale X-ray vision, revealing what lies hidden beneath an unassuming surface. Ground-penetrating radar, or GPR, is one of the most powerful of these tools. It works by sending high-frequency radio waves into the ground and listening for the echoes as they bounce off different layers of soil, rock, and crucially empty spaces. By dragging a GPR unit over the ground in a careful grid, researchers can create a detailed subsurface profile, identifying the telltale signatures of tunnels, caverns, and sediment-filled passages without ever lifting a shovel. This technology is indispensable for archaeologists investigating buried structures near cave mouths, but it's also vital for pure geological research, helping to trace the hidden extent of a known cave system far beyond its known endpoints. For the most ambitious projects, scientists are even turning to satellite-based radar and gravity meters. These incredible instruments can detect minute changes in the Earth's gravitational field or surface elevation that betray the presence of massive, hidden voids below. A slight dip in the gravitational pull in an area or a subtle sinking of the ground surface can be the only clue needed to pinpoint a colossal cave system waiting to be found, proving that some of the greatest discoveries now begin not with a daring descent, but with a subtle anomaly on a satellite data readout. All of this raw data, the billions of laser points, the radar echoes, the gravitational readings, would be an incomprehensible mess without the final piece of the technological puzzle: sophisticated 3D modeling software. This is where data transforms into understanding. Powerful computers compile all this information into intricate, navigable digital worlds. A speleologist can now put on a virtual reality headset and literally fly through a photorealistic model of the Lechuguilla cave system in New Mexico, a place so fragile and remote that only a handful of people will ever physically visit its deepest chambers. They can zoom in to examine the delicate texture of a wall to study erosion patterns, or zoom out to see how an entire network of passages aligns with a major geological fault line. This is the key to testing our magnetic reversal hypothesis. With these perfect digital twins, scientists can perform detailed spatial analysis with a precision that was once unimaginable. They can measure the exact volume of a chamber, calculate the rate of sediment deposition in a passage, and most importantly, correlate the precise geological age of different cave sections obtained from dating stalagmites with their physical structure. This allows them to ask a direct question: did the parts of the cave that show evidence of extremely rapid, violent formation, where rock was massively scoured away or huge collapses occurred, form during the known dates of a geomagnetic reversal? The digital model provides the spatial context. The paleomagnetic data from the rocks provides the timing. For the first time, we can truly begin to map the pulses of planetary chaos onto the architecture of the underworld. The proof of this powerful synergy is already emerging from the most challenging environments on Earth. The ambitious project to map the vast underwater labyrinths of the Yucatan Peninsula's cenotes is a perfect example. Here, cave divers equipped with underwater LiDAR and sonar mapping devices are charting the world's most extensive flooded cave systems, revealing hundreds of miles of interconnected tunnels. As they map, they are discovering layers of sediment that contain ancient evidence of water level changes and massive collapse events. By correlating the timing of these dramatic physical changes with the paleomagnetic record locked into the limestone walls themselves, researchers are beginning to see a compelling pattern where periods of upheaval in the caves align with periods of instability in Earth's magnetic field. Similarly, the ongoing, decades-long effort to map the immense and incredibly complex Lechuguilla cave has been supercharged by 3D laser scanning. The resulting model is so precise that geologists can virtually analyze the orientation of every fault and fissure that control the cave's development, searching for patterns that might indicate a period of intense tectonic stress, the kind that could be triggered by the crustal heating from increased radiation during a magnetic crash. This isn't just mapping for the sake of it, it's a sophisticated forensic investigation. Each digital scan, each radar profile, is another piece of evidence presented in the greatest cold case of all time, helping us to finally understand the forces that built the hidden, beautiful, and mysterious world beneath our feet. Now, this idea that the collapse of our planet's magnetic shield could act as a great accelerator for cave formation is a fascinating and compelling narrative, but it's crucial to step back and recognize that within the scientific community, this hypothesis is far from settled fact. It exists squarely in the vibrant and often contentious arena of theoretical geophysics, where intriguing correlations are met with healthy skepticism and demands for more robust evidence. The central challenge, as many critics point out, is the sheer, overwhelming complexity of geological systems. Isolating a single driver like a magnetic reversal from the constant, chaotic symphony of other forces is like trying to identify one instrument in a full orchestra during a thunderstorm. The rock record is incredibly noisy, and proving causation rather than just coincidence is the highest and most difficult bar to clear. Many geologists who specialize in karst processes, the formation of landscapes by the dissolution of soluble rock, argue that the established, purely hydrological and tectonic mechanisms are more than sufficient to explain the existence of even the most massive cave systems. From this perspective, the incredible scale of a place like Mammoth Cave is simply a function of three things: an immense thickness of pristine limestone, a vast amount of time, and a consistent and plentiful water supply. They posit that the observed periods of accelerated growth in speleothems could be explained by more conventional, well-understood climatic shifts, like the cyclic advance and retreat of ice ages driven by changes in Earth's orbit known as Milankovitch cycles. These cycles dramatically alter sea levels and precipitation patterns over regular intervals and leave a clear, predictable signature in the geological record that doesn't require an extraterrestrial trigger from cosmic rays. As one prominent karst scientist might argue, why invoke a novel and difficult-to-prove mechanism when the tools we already have in our toolbox, hydrology, tectonics, and orbital forcing, do an excellent job of explaining 99% of what we see? We must be wary of the allure of a sexy story over Occam's razor. The alternative explanations are powerful in their own right. The purely hydrological model emphasizes that water will always find a way given enough time. The initial pattern of fractures in the rock, often created during the mountain-building events that lifted the limestone plateaus millions of years ago, provides the initial blueprint. From there, gravity-driven water flow, chemical saturation levels, and the base level of nearby rivers do the rest of the work in a slow, relentless, and predictable manner. Meanwhile, the tectonic argument is equally strong. Major seismic events unquestionably shatter bedrock and create new pathways in an instant. A single large earthquake along a fault line can open up miles of new fractures for water to exploit, and this can happen at any time, completely independent of what the magnetic field is doing. The question for proponents of the magnetic theory then becomes not whether these other processes work, but whether they are enough to explain the observed rapid growth phases. Is there a missing piece of the puzzle that acts as a periodic supercharger? This is where the debate gets into the finer details of evidence. A skeptic might look at the data and say the correlations are simply not tight enough. The timing of magnetic reversals is known from volcanic rocks, but these dates have margins of error that can span thousands of years. The uranium-thorium dates from cave formations also have their own, smaller margins of error. Getting these two timelines to align perfectly is exceptionally difficult. Could an apparent correlation be just a lucky coincidence, where a period of heavy rainfall from a more mundane weather pattern just happened to occur around the same time, geologically speaking, as a magnetic wobble? It's entirely possible. Furthermore, the proposed physical mechanism, that increased cosmic radiation could significantly heat the crust or disturb the mantle, is hotly debated. Some physicists model that the energy input, while real, is simply too minuscule to have any measurable effect on the vast, energetic systems of plate tectonics or deep-seated volcanism. The forces at work in the mantle are orders of magnitude greater, adding a tiny bit of surface heating would be like trying to steer a supertanker by spritzing the deck with a water pistol. Yet, the researchers championing this idea are not deterred. They acknowledge the challenges but point to the growing body of multi-proxy evidence that is hard to ignore. It's the convergence of clues that they find compelling. The fact that we see signals in ice cores, ocean sediments, and cave formations all pointing to global environmental upheaval at the same moments in time. They argue that while the energy input from cosmic rays may be small, complex systems can have tipping points where a small perturbation can trigger a large-scale response. As one proponent of the theory might counter, we're not saying it's the only driver, but it could be the critical catalyst that pushes a stable system into a new dynamic state. The simultaneous evidence for climate shifts, increased seismicity, and accelerated cave formation is a pattern that demands investigation, not dismissal. This honest, vigorous debate is not a weakness of the scientific process, it is its greatest strength. It forces everyone to sharpen their arguments, seek better data, and remain open to being proven wrong. This ongoing conversation ensures that our understanding of the planet, from its core to its caves, continues to evolve, driven by a shared sense of wonder and a relentless pursuit of the truth. Right now, as we speak, the very shield that protects our planet is showing signs of significant strain. Earth's magnetic field has been weakening at an alarming rate, losing roughly 5% of its strength every single century for the past several hundred years. This isn't a subtle, background hum of change. It's a pronounced and measurable decline that has scientists around the globe paying very close attention. This weakening is most dramatically visible in a vast region stretching from South Africa to South America, known as the South Atlantic Anomaly. Here, the field is already so unusually weak that satellites and spacecraft passing through it have to power down their sensitive instruments to avoid permanent damage from the increased radiation that bleeds through. This isn't a prediction of a distant future. This is a present-day reality with tangible consequences for our technology. The big, looming question that hangs over all this data is a profound one. Are we currently in the early, slow-motion stages of a full geomagnetic reversal? The evidence suggests it's a distinct possibility. While the complete process from start to finish could easily take 1,000 years or more, the initial phases of instability and decay are exactly what we appear to be witnessing right now. For our hyper-connected, technology-dependent modern civilization, the practical implications of a drawn-out magnetic collapse would be far more than just an academic curiosity. They would pose a direct and multifaceted challenge to the very infrastructure of our daily lives. The most immediate and severe impact would be on our global network of satellites, which have become the invisible backbone of everything from GPS navigation and international finance to weather forecasting and global communications. These delicate machines orbit high above the Earth, largely protected by our magnetic bubble from the sun's relentless particle wind. As that bubble weakens and frays, more of that high-energy radiation would pour into their orbits, frying sensitive electronics, degrading solar panels, and drastically shortening their operational lifespan. We would be facing a future where replacing crucial satellites becomes a constant, expensive battle against the elements of space. Closer to the ground, the danger shifts to our planet-wide power grid. Intense solar storms, which our weakened shield would be less able to deflect, could induce massive electrical currents in long-distance power lines. This isn't a theoretical risk. A much smaller event in 1989, the Quebec blackout caused by a solar storm, left millions in Canada without power for 9 hours. A major storm during a period of extreme magnetic weakness could trigger a cascading failure of transformers and substations, potentially leading to continent-wide blackouts that could take months or even years to fully repair. Beyond the lights going out, our constant reliance on precise GPS timing for everything from cellular networks to air traffic control would be thrown into chaos, introducing errors that could ripple through every sector of the economy. The modern world is built on a foundation of electromagnetic stability, and a reversal would systematically undermine that foundation. But the potential consequences might extend beyond our circuits and screens, reaching down into the very geology of the planet itself. If the theories we've been exploring hold true, that past periods of magnetic turmoil were linked to increased tectonic and volcanic activity, then we must consider what a future reversal might awaken. The additional energy input from increased radiation could, as a catalyst, potentially influence the delicate balance of stresses within the Earth's crust and mantle. This could translate into a statistically significant rise in the frequency or intensity of seismic events in already volatile regions. We might see more powerful earthquakes as fault systems are nudged past their breaking points. Similarly, the increased heat flow and destabilization could lead to more frequent volcanic eruptions as magma finds it easier to force its way to the surface. This wouldn't mean volcanoes suddenly appearing in the middle of Kansas, but it could mean that the famously active rings of fire around the Pacific and the Atlantic become even more restless, with longer eruptions and shorter periods of dormancy. The ash clouds and climatic disruptions from such events would themselves have profound secondary effects on global agriculture and weather patterns, creating a complex web of challenges that would test the resilience of societies worldwide. This brings us back to the grand geological mystery of the underground labyrinths. If we are indeed standing at the beginning of a millennia-long magnetic transition, what legacy might this event leave on the physical planet long after our cities and our names are forgotten? The processes we suspect accelerated cave formation in the past, increased rainfall from climate shifts, more frequent earthquakes fracturing the bedrock, heightened volcanic activity creating new lava tubes, would all be set into motion once again, operating on their own unimaginably slow time scale. The heavy, ionizing rains of a magnetically disturbed climate would begin their patient, acidic work on the great limestone plateaus of the world, seeking out new fractures. Each major earthquake along the planet's fault lines would not be just a news event, but a geological event pulverizing rock and opening vast new networks of pathways deep underground. The increased volcanic output would birth a new generation of extensive lava tube systems, their formation recorded in the reversed magnetic signature of their basalt walls. Over the next 10,000 or 50,000 or 100,000 years, this period of magnetic chaos could act as a great period of subterranean construction, sculpting a new generation of labyrinthine networks that would remain hidden from the surface for eons. Future intelligent species, whatever they may be, might one day explore these caves, drill into their stalagmites, and analyze the magnetic minerals within. They would find a clear, sharp signal of a field in collapse, a period of planetary instability, and they would rightly conclude it was a time of great change. They might even theorize, as we have, that this magnetic crash was the very architect of the beautiful, twisting maze they now stand within, forever linking the invisible turmoil of the core to the enduring architecture of the crust. But as we stand in awe of these underground cathedrals, carved over millions of years by forces both patient and cataclysmic, we must also recognize a profound and urgent responsibility. These are not indestructible monuments. They are among the most fragile and non-renewable resources on our planet. A single, delicate stalactite that took 100,000 years to form can be shattered by a careless touch in an instant. The scientific value locked within these labyrinths is simply incalculable. They are pristine climate archives holding detailed records of past rainfall, temperature, and atmospheric composition in the layers of their speleothems with a resolution that often surpasses ice cores or ocean sediments. They are unique biological laboratories hosting ecosystems of specially adapted, often blind and colorless creatures, from translucent cavefish to exotic bacteria that have evolved in complete isolation, offering potential breakthroughs in medicine and our understanding of evolution itself. And as we've explored, they may even be silent witnesses to the most dramatic events in Earth's deep history, holding magnetic minerals that could help us finally understand the full impact of a geomagnetic reversal. To lose these places is to burn entire chapters of our planet's autobiography before we've even had a chance to read them. The threats they face are as varied as they are severe, and many are accelerating at an alarming pace. Pollution is a silent and insidious killer. Contaminated surface water can carry agricultural chemicals, industrial waste, and sewage directly into the delicate underground environment through the same sinkholes and fissures that feed the system. This poisons the unique aquatic life and can permanently alter the chemical balance needed for speleothem growth. Perhaps the most pervasive threat is the one we've been discussing: human-driven climate change. Altering precipitation patterns can either starve a cave of the water it needs to continue its slow growth or, conversely, deluge it with such intense, erosive flows that it damages existing formations. Rising sea levels are already flooding coastal cave systems like those in the Yucatan, dissolving their walls and wiping out their ecological and geological records. Then there is the direct impact of human intrusion. While responsible caving and tourism can foster appreciation, unsustainable practices lead to trail erosion, the introduction of foreign materials, and the devastating spread of fungal pathogens on footwear that can wipe out entire colonies of bats, which are themselves critical pollinators and pest controllers for ecosystems above ground. This is where our journey from the planet's core to its crust comes full circle, transforming from pure discovery into actionable stewardship. The very science that helps us understand how these labyrinths formed, including the potential role of magnetic crashes, also provides the essential tools for their protection. By meticulously studying the paleomagnetic and climatic records within stalagmites, scientists can establish a precise baseline for a cave's natural hydrological cycle. This allows conservationists to immediately detect when something is wrong, when water flow or chemistry changes in a way that falls outside of millions of years of natural variation, signaling a new human-caused stressor. This deep historical knowledge turns each cave into its own canary in the coal mine, providing an early warning system for the health of the entire regional environment. Thankfully, a global movement of scientists, conservationists, and dedicated cavers is rising to meet this challenge through a powerful combination of technology, policy, and grassroots passion. Sophisticated monitoring is now a cornerstone of protection. Networks of wireless sensors are being installed in sensitive caves to continuously track temperature, humidity, carbon dioxide levels, and water quality, transmitting real-time data to researchers who can spot problems the moment they arise. The designation of protected areas like national parks and World Heritage Sites provides a crucial legal framework to shield these wonders from destructive development and resource extraction. Perhaps most inspiring are the initiatives focused on gating. This isn't about locking the public out. It's about installing specially designed, bat-friendly gates that restrict access to the most fragile sections of a cave while still allowing wildlife to move freely and researchers to continue their vital work. These efforts are often led by non-profit organizations like the National Speleological Society or the Cave Research Foundation, groups powered by the volunteer efforts of people who love these hidden worlds and are determined to save them. The call to action extends to every single one of us. We can choose to be mindful tourists, seeking out guided tours that follow strict leave no trace principles and support the local economies that benefit from preserving these natural wonders. We can advocate for stronger environmental protections and support the organizations on the front lines of cave conservation through donations or volunteer work. We can even become citizen scientists, contributing to projects that help map and monitor these systems. The story of Earth's underground labyrinths is still being written. It is a narrative of fire, ice, water, and perhaps cosmic magnetism. By choosing to protect these places, we ensure that this incredible story won't end with our chapter, but will continue to be read and wondered at by generations to come, long after our own footprints on the surface have faded away. What if the most compelling classroom for understanding our planet isn't a textbook, but a journey into the underworld? The story of Earth's magnetic crashes and the labyrinthine caves they may have sculpted offers a breathtakingly powerful framework for education, a narrative thread that can tie together the entire tapestry of Earth science. This isn't just a niche topic for specialists. It's a master key that unlocks student engagement by connecting the invisible forces of the core to the tangible wonders beneath our feet. Imagine a lesson on plate tectonics that doesn't just describe how plates move, but explains how the stress from a shifting mantle, potentially amplified by a weak magnetic field, can fracture an entire continent's bedrock, creating the very blueprint for a future cave system. Suddenly, an abstract concept has a physical, explorable consequence. A unit on climate change takes on a deeper historical context when students analyze speleothem records, seeing for themselves how past planetary upheavals altered rainfall patterns and left their mark in the growth rings of a stalagmite. This approach transforms science from a collection of isolated facts into a dynamic, interconnected story where physics, geology, chemistry, and biology are all essential characters. The real magic happens when this story moves from the page into students' hands through immersive, project-based learning. A teacher could bring paleomagnetism to life with a simple but powerful activity. Students can create their own lava by melting paraffin wax mixed with iron filings in a shallow pan. As the wax cools and solidifies, they use a strong magnet to align the filings, mimicking how magnetic minerals freeze in place within real lava. Then the reveal, they carefully break the wax and use a compass to read the magnetic direction their sample recorded. Now, imagine a second group does the same activity, but while their wax is cooling, the teacher has them slowly move the aligning magnet to simulate the wandering poles during a reversal. When the two groups compare their results, they don't just hear about magnetic reversals. They hold the evidence in their hands, seeing one sample with a clear, strong signal and the other with a weak, scrambled one. This tangible experience demystifies complex data and makes the process of scientific discovery feel immediate and authentic. For the geological side of the equation, the possibilities for hands-on exploration are equally rich. Modeling cave formation can be as simple as using a block of plaster of Paris or even a large piece of chalk to represent soluble limestone. Students can drip a weak acid-like vinegar onto the surface and observe how it slowly dissolves the material, creating tiny pits and channels. To simulate the accelerated erosion during a period of magnetic instability and heavy rainfall, they can use a spray bottle to saturate the entire block, watching how the water finds and rapidly enlarges every tiny weakness. More advanced classes can even construct physical or digital models of watersheds to test how changes in precipitation, driven by theoretical climate shifts, alter groundwater flow and dissolution rates in a karst landscape. These activities do more than teach a single principle. They build a holistic understanding of systems thinking. Students aren't just learning that water dissolves rock, they're seeing how a change in the atmosphere, triggered by an event in Earth's core, can directly impact the architecture of the subsurface, fostering a profound appreciation for the delicate and dynamic balances that govern our planet. Ultimately, the greatest educational gift this topic offers is its perfect illustration of science as a living, breathing, and wonderfully unfinished process. Presenting the debate between the established hydrological theories of cave formation and the more novel magnetic catalyst hypothesis is a golden opportunity to teach critical thinking. Educators can provide students with simplified datasets, graphs of speleothem growth rates alongside the paleomagnetic record, or maps of volcanic activity timelines, and guide them through the process that real scientists use. They can ask the essential questions: does the correlation imply causation? What other factors could be at play? What kind of additional evidence would you need to be more convinced? This moves learning beyond memorization and into the realm of evaluation and argument, showing that science isn't a static set of answers but a continuous, evidence-based conversation. It empowers students to see themselves not as passive recipients of knowledge, but as potential future contributors to a mystery that is still being solved. By grounding colossal planetary concepts in the relatable mystery of exploring a dark, twisting cave, we can ignite a lifelong curiosity about the forces that shape our world, creating not just better students, but more informed and awestruck citizens of Earth. To truly appreciate the scale of this geological mystery, we need to embark on a global tour to see with our own eyes, or at least through the eyes of intrepid explorers, that these underground labyrinths are not a local curiosity, but a planetary phenomenon. Their widespread presence, from isolated islands to continental interiors, suggests that if there is a singular catalyst for their most explosive periods of growth, it must be a force equally universal in its reach. Our first stop takes us to the South Pacific, to the Waitomo glowworm caves on New Zealand's North Island. This is a labyrinth of a different kind, where the primary sculptor is the relentless flow of the Waitomo River, which has carved a breathtaking network of limestone passages and caverns over millions of years. But the true magic of Waitomo is its living ceiling, a starry night sky created by the bioluminescent glow of thousands of tiny fungus gnat larvae. While the cave's formation is a masterpiece of hydrological patience, studies of the region's volcanic activity and sediment deposition suggest periods of intensified erosion that intriguingly overlap with known dates of past magnetic field excursions, hinting that even this serene, glowing world may have been shaped by moments of ancient cosmic turmoil. Journeying north to the island of Mallorca, Spain, we find another type of water-carved wonder, but one with a dramatic twist. The Coves del Drac, or Dragon Caves, are a spectacular flooded labyrinth stretching for over 2.4 kilometers, home to one of the largest underground lakes in the world. What makes this system particularly fascinating to scientists is its intimate connection to sea level change. As the Mediterranean Sea rose and fell with the pulse of the ice ages, the water table within the cave fluctuated dramatically, leaving clear horizontal lines on the cave walls that mark ancient shoreline. Detailed analysis of the mineral deposits here has allowed researchers to construct a precise timeline of these flooding events. Some of the most pronounced phases of cave decoration and enlargement appear to correlate with periods of rapid sea level rise, which themselves may have been influenced by the climatic instability triggered by geomagnetic reversals, creating a tangible link between the chaos in the magnetic field and the water levels in this subterranean sea. Now let's shift from the serene to the immense, In the heart of Ukraine, near the border with Romania, lies a labyrinth that defies all scale and expectation, Optimistichna Cave. This is not a cave system for casual tourists. It is a sprawling, claustrophobic, and incredibly complex maze within a thick layer of gypsum, a much softer and more soluble rock than limestone. With over 230 kilometers of mapped passages and believed to extend much farther, it is the longest gypsum cave in the world and the second longest cave of any kind in Eurasia. Its name, Optimistic Cave, was given by its discoverers in 1966 as a tongue-in-cheek response to skeptics who thought their prospects of finding a significant system were overly optimistic. The cave is a chaotic, multi-level warren of tiny, water-sculpted tunnels, often no wider than a human body, creating a truly otherworldly environment. The sheer volume of this maze, carved so quickly in geologically terms by the rapid dissolution of gypsum, poses a profound question. Some researchers point to evidence that its most active development phases may have occurred during periods of heightened hydrological activity, potentially driven by the same global climate shifts that magnetic reversals can produce, suggesting that even this uniquely vast and strange labyrinth might bear the faint fingerprints of a planetary event. Crossing the Atlantic, we find a labyrinth born not from gentle water but from unimaginable heat and violence. The Kazumura Cave System on the Big Island of Hawaii holds the title of the longest and deepest lava tube in the world, an incredible 65.5 kilometers long and descending over 1,100 meters from its highest entrance. This is a cave forged in a single, furious event, a cast of a river of fire that once flowed from the mighty Kilauea volcano. Walking through Kazumura is like walking through a snapshot of that apocalyptic moment. The walls are often glassy smooth, decorated with lava falls, shelves, and even hardened waves. The connection to magnetic activity here is not through water, but through the fire that created it. Paleomagnetic analysis of the cave's basalt walls can instantly reveal if the lava flow that formed it occurred during a period of stable or reversed polarity. While dating such a specific flow is complex, the broader volcanic pulses that create these immense tubes are a key area of study for those investigating links between mantle activity and magnetic field behavior, making Kazumura a direct monument to the potential conversation between the core's dynamo and the volcanism it may influence. Finally, we venture to the shallow, warm seas of the Bahamas, to a labyrinth that is almost entirely hidden beneath the waves. The blue holes of the Bahamas are not caves in the traditional sense, but vertical sinkholes and caverns that open on the seafloor, leading to vast, flooded passageways that tunnel through the carbonate bedrock. These include wonders like Dean's Blue Hole, the deepest known sinkhole of its kind, plunging over 200 meters into darkness. These submerged labyrinths are particularly sensitive recorders of past sea levels. As the ocean rose after the last ice age, it flooded these caves, preserving within them a stunningly detailed archive of past climate conditions in the layers of sediment on their floors and the chemistry of their stalactites, which now grow underwater. Core samples extracted from these sediments are being meticulously studied, and some show distinct layers from periods of rapid environmental change. Researchers are now cross-referencing these layers with the paleomagnetic record, searching for clues that could tie the flooding of these sunken kingdoms to the grand, planetary disruptions caused by a faltering magnetic field. From the glowing ceilings of New Zealand to the flooded depths of the Bahamas, this global tapestry of labyrinths presents a consistent and compelling pattern. They are found on every continent, in every type of soluble rock, and under every conceivable climate. The fact that so many of them show evidence of punctuated, rapid growth that broadly aligns with Earth's periods of magnetic instability is a thread that connects them all, pointing toward a universal driver behind the planet's most secret and spectacular architecture. This incredible story of magnetic crashes and hidden labyrinths reveals a profound truth about modern science. The most groundbreaking discoveries are no longer made within the isolated silos of a single discipline. They are born in the vibrant, collaborative spaces where different fields converge, each bringing its own unique language, tools, and perspective to a shared mystery. Unraveling a planetary puzzle of this scale requires a symphony of expertise, not a solo performance. It demands that a geologist who can read the story in a rock layer must learn to speak the language of a physicist who models the chaotic flow of liquid iron in the core. It requires a climatologist studying ancient ice cores to compare notes with a geochemist analyzing the isotopes in a stalagmite. This is no longer just geology. It is a grand, interdisciplinary fusion where the boundaries between fields blur, creating a new and more powerful way of understanding our world. At the heart of this collaboration are the physicists and astrophysicists who provide the fundamental rules of the cosmic game. They are the ones who can calculate the precise amount of energy delivered to Earth's atmosphere when the magnetic shield weakens, modeling how those increased levels of solar wind and cosmic radiation interact with our planet's protective layers. Their complex simulations help us understand the chain reaction, how a surge in cosmic rays can seed cloud formation, which in turn alters albedo and atmospheric circulation patterns, potentially shifting global climate into a new state. Without their sophisticated models, the connection between a magnetic collapse and a change in rainfall over a cave in Kentucky would remain a vague speculation. They provide the rigorous mathematical framework that turns a fascinating correlation into a testable physical hypothesis, quantifying the invisible forces that initiate this entire cascade. Then there are the geochemists, the master detectives of the material world. While a geologist might point to a layer of broken rock and see evidence of an ancient earthquake, the geochemist can drill into a stalagmite and uncover a detailed history of the water that flowed through the cave when that quake happened. Their toolbox is incredible. They use mass spectrometers to measure the precise ratios of oxygen isotopes within each layer of calcite, which act as a paleothermometer, revealing the temperature at the time that layer formed. They analyze traces of ancient rainfall trapped in fluid inclusions, tiny bubbles of water frozen in time within the stone. Most importantly for our story, they are the ones who can extract and isolate the microscopic magnetic minerals, the magnetite and hematite grains, from tons of cave sediment or from within the speleothem itself. They meticulously clean and prepare these tiny time capsules so that the physicists with their ultrasensitive magnetometers can then read the magnetic story locked inside. This partnership is essential. One field provides the pristine evidence and the other interprets its meaning. We can see the stunning success of this interdisciplinary approach in specific landmark studies. Consider the research into the Labyrinths excursion. The initial evidence came from paleomagnetists studying volcanic rocks in France, but that was just a single point on the map. To understand the global impact, climatologists then analyzed ice cores from Greenland and Antarctica, finding the telltale spike in beryllium-10 that confirmed the event was worldwide. Meanwhile, archaeologists contributed by radiocarbon dating artifacts and human remains from that era, helping to build a timeline of how human societies might have been affected. And now, speleologists are adding the final, crucial piece by examining stalagmites from caves across Europe and Asia that were growing during that exact period. By combining the magnetic data from the speleothems with the climate data from their chemistry, they can directly correlate the magnetic field's collapse with a dramatic change in precipitation patterns on the surface. This isn't a chain of discovery, it's a woven tapestry where each thread from a different field strengthens the overall picture. This beautiful synergy extends beyond the immediate puzzle, often leading to unexpected and revolutionary side discoveries. The need to precisely date cave formations drove advancements in uranium-thorium dating techniques, pushing geochemistry to new levels of precision. The challenge of mapping impossibly complex cave networks in 3D accelerated the development of LiDAR and ground-penetrating radar technology, innovations that now benefit everything from archaeology to urban planning. And the study of the unique, isolated ecosystems found in these labyrinth life forms that have evolved for millennia in total darkness has become a cornerstone of astrobiology, helping NASA as scientists understand what life might look like in the subsurface oceans of moons like Europa or Enceladus. The collaboration to solve one mystery about our own planet has literally given us the tools to search for life on others. This is the true power of interdisciplinary science. It creates a whole that is vastly greater than the sum of its parts, proving that the biggest questions about our planet and our place in the universe can only be answered when we finally learn to work together. Of course, the most dramatic ideas are often the ones that capture our imagination, painting pictures of overnight catastrophes and worlds turned instantly upside down. It's easy to fall into the trap of imagining a geomagnetic reversal as a single catastrophic event, a literal flip of a switch that happens in a blinding instant, plunging the planet into immediate chaos. This vision, popularized by sensationalized doomsday scenarios, suggests everything from instant climate collapse to mass extinctions occurring within a human lifetime. The reality, as the geological record patiently tells us, is far more gradual, complex, and in its own way, even more fascinating. A full polarity reversal isn't a sudden snap. It's a prolonged, messy period of transition that unfolds over centuries and more typically over 1,000 or 2,000 years. That's longer than the entire span from the fall of the Roman Empire to today. During this extended wobble, the magnetic field weakens and becomes disorganized, but it doesn't vanish entirely. Life on Earth has weathered hundreds of these events, and the fossil record shows no clear link to major extinction events, suggesting that while it presents challenges, it is not an automatic apocalypse. The real risks are to our fragile technological infrastructure, not to life itself, and they unfold on a timescale that allows for adaptation and mitigation. This same principle of immense, patient timescales applies directly to the formation of the underground labyrinths we've been exploring. No cave system, no matter how vast or complex, was carved in a single, violent geological event. The idea that a period of magnetic instability could suddenly create a labyrinth-like Mammoth cave is a fundamental misunderstanding of the process. What the science suggests is not instant creation, but a period of accelerated excavation. Think of it like this: the cave's blueprint, the initial network of fractures and weaknesses in the rock was already there, laid down by tectonic forces millions of years earlier. For eons, water has been slowly, patiently tracing over those lines, dissolving the rock grain by grain. The hypothesis is that during a magnetic reversal, the external catalyst of climate change and potentially increased seismic activity acts like a supercharger for this process. It doesn't draw a new maze, it takes the existing, faint sketch and traces over it with a much thicker, more powerful pen. The water flows faster and in greater volume, the earthquakes open up fractures more widely, and the entire system expands at a rate that is rapid in geological terms, but would still be utterly imperceptible to any human observer. A single, massive storm during this period might wash away a ton of dissolved rock that would have taken a century to move under normal conditions. This is how you build 400 miles of passage, not in a day, but through countless moments of accelerated effort stretched over millennia. Perhaps the most pervasive and understandable myth is the fear that a weakened magnetic field would leave us completely exposed to lethal radiation from the sun, sterilizing the surface of the planet. This fear stems from a confusion between different types of solar emissions. Our atmosphere itself is a remarkably robust shield, particularly against high-energy electromagnetic radiation like X-rays and ultraviolet light. It's this atmospheric layer that does the primary work of protecting us from the sun's everyday fury. The solar wind, which is deflected by our magnetic field, consists mostly of charged particles like protons and electrons. While an increased flux of these particles would indeed pose a significant hazard to astronauts in orbit and could damage satellites and power grids, it is largely stopped by the miles of air above our heads. The evidence for this is written in our own DNA. Our ancestors lived through the Labyrinths excursion 41,000 years ago, and while they may have witnessed breathtaking auroras reaching down to the equator, they clearly survived the experience. The real narrative isn't about the end of the world. It's about the resilience of life and the challenges of maintaining a high-technology civilization in a dynamic solar system. Separating this compelling science from the shadow of fiction is not about dismissing people's curiosity or fear. It's about redirecting that energy towards a much more profound sense of wonder. The truth is, in many ways, more staggering than the myth. The fact that our planet possesses a dynamic, living core that can reset its own magnetic compass is incredible. The idea that the faint, invisible force lines of this field could interact with the climate system, influencing rainfall patterns that then dictate the pace of cave formation deep underground, is a breathtakingly beautiful connection. It links the most profound depths of our planet to its atmosphere and beyond to the sun itself in a single, interconnected system. This isn't a simple, scary story of a switch flipping. It's an epic, multi-million-year saga of planetary evolution. By letting go of the sensationalized Hollywood version, we open ourselves up to the genuine awe of the real story. A slow, majestic dance of cosmic and terrestrial forces that has been sculpting the hidden architecture of our world in the darkness, leaving a record of its passage not in instant cataclysm, but in the patient, layered growth of a stalagmite and the silent, magnetic memory of stone. After journeying through these vast, hidden worlds from the comfort of your screen, you might be feeling the pull to experience their silent majesty for yourself. The call to explore is a powerful one, and with the right approach, you can answer it safely and responsibly, becoming not just a visitor but a guardian of these fragile realms. The single most important rule for any aspiring cave explorer is to never go it alone. Your first step should always be to connect with your local grotto of the National Speleological Society or an equivalent caving organization in your country. These groups are filled with experienced, passionate cavers who are eager to mentor newcomers. They organize regular, supervised trips for all skill levels, from easy walking caves to more technical vertical descents. This isn't just about safety in numbers, it's about learning the culture of caving, a culture built on conservation, teamwork, and respect. For your very first taste of the underground, seek out a commercially operated show cave. These professionally managed sites offer guided tours on safe, well-lit pathways, allowing you to witness breathtaking formations and grasp the immense scale of these environments without any of the risk or specialized gear. It's the perfect introduction, a chance to stand in awe of a giant cavern room and feel the cool, still air on your face, confirming that yes, this is something you absolutely want to pursue further. If that initial experience solidifies your interest, the next step is gearing up correctly, and this goes far beyond a simple helmet and headlamp. the essential piece of equipment is a quality caving helmet, specifically designed for underground use with a chin strap and a mounting bracket for not one, but two independent primary light sources. Your life literally depends on your ability to see in absolute darkness, so redundancy is non-negotiable. This means a bright LED headlamp mounted on your helmet with fresh batteries, plus a second, equally powerful backup light attached to your person. Many cavers also carry a third, small emergency light like a waterproof handheld flashlight. Your clothing should be durable, made of synthetic materials or wool that will insulate even when wet cotton is a dangerous choice as it saps body heat. Knee pads and sturdy, lug-soled boots with good ankle support are not luxuries. They are absolute necessities for protecting your body against the abrasive, often sharp rock you will be crawling and climbing over. For any trip beyond a simple walk in cave, you'll need a helmet-mounted GoPro to capture the experience without using your hands. Before you even think about entering a wild cave, practice with your gear. Sit in a pitch-black closet at home and try to change the batteries on your headlamp using only your backup light. This simple drill will instantly show you why preparation is everything. Once you're properly equipped and with a group, your mindset underground must shift to one of hyper-awareness and minimal impact. Every action you take should be guided by the principle of leaving no trace. This means staying on established trails to avoid crushing fragile cave life like bacteria colonies or delicate gypsum crystals, which can be destroyed by a single misplaced step. Be meticulously careful not to touch formations. The oils, dirt, and acids on your skin can permanently stain a pristine stalactite and halt its growth forever. A moment of carelessness can erase 100,000 years of patient development. Keep your voice low. The silence of a cave is part of its magic, and loud noises can be stressful for its resident wildlife, like bats. If you encounter bats, especially during hibernation season in winter, give them a wide berth. Waking a bat from hibernation forces it to burn crucial fat reserves it needs to survive until spring. Perhaps the most thrilling way to deepen your exploration is to participate in a citizen science project. Many cave conservation groups and research institutions organize trips where volunteers can help with tasks like mapping new passages, counting bat populations, or even helping to carefully clean and document ancient artifacts found in caves. This transforms your adventure into a direct contribution, allowing you to be part of the ongoing story of discovery and preservation, ensuring these incredible labyrinths remain intact and understood for the generations of explorers and scientists who will follow in your footsteps. It's a comforting image to think of science as a perfectly straight line, a logical march from question to hypothesis to experiment to definitive answer. But the reality is far more exciting and human. The path of discovery is rarely a straight line. It's a labyrinth filled with unexpected twists, dead ends, and every so often, a chance turning that leads to a revelation no one could have predicted. Some of the most pivotal breakthroughs in our understanding of the planet, from the very nature of its core to the secrets hidden in its deepest caves, have come not from a rigid plan, but from a moment of pure, unplanned serendipity. Consider the story of the Labyrinth excursion itself, the key piece of evidence for a recent magnetic flip. It wasn't discovered by a scientist who set out to find it. In the 1960s, researchers were studying a lava flow near the tiny village of Labyrinths in France. They were taking routine paleomagnetic measurements, expecting the rock to show the standard magnetic north alignment. But their instruments went haywire. The needle didn't point north, it pointed south. At first, they likely assumed it was an error, a faulty instrument, or a contaminated sample. But upon painstaking repetition, the result held. They had accidentally stumbled upon a lava flow that had recorded a complete but temporary reversal of Earth's magnetic field. A routine investigation, a baffling anomaly, and a willingness to trust the strange result led directly to the identification of one of the most significant geomagnetic events in recent history. This spirit of accidental discovery is just as alive in the world of cave exploration. The story of Lechuguilla Cave in New Mexico is a perfect testament to this. For decades, it was considered a small, insignificant hole in the ground, known only for the packrat bones and a constant, foul-smelling breeze that wafted from its narrow entrance. Most cavers wrote it off, but that breeze was the clue. A small group of persistent explorers wondered where that air was coming from. It suggested a vast, unknown space on the other side of the rubble that choked the entrance. In 1986, after years of negotiation and effort, they were granted permission to dig. What they found wasn't just a new cave, it was a subterranean continent of staggering beauty and scientific value. Their curiosity about a funny smell led to the discovery of over 150 miles of pristine passages, a time capsule of geological processes and unique microbial life that has utterly transformed our understanding of how caves form in arid environments. They weren't looking for the world's most spectacular cave, they were just following a hunch, a whisper of air from the darkness. This is the beautiful, messy truth of science. It advances as much on prepared curiosity as on meticulous planning. A researcher drilling a core from a stalagmite might be focused on climate data, but notices an odd, gritty layer within the pristine calcite. Instead of dismissing it as contamination, they decide to analyze the magnetic minerals in that grit, and suddenly they've added a crucial new day to point to the paleomagnetic record. A caver squeezed into a tight passage might notice that the rock on one side feels strangely different, smoother, or of a different color. Choosing to investigate that slight variation instead of pushing forward can lead to the discovery of an entirely new fossil passage that no water has flowed through for 1,000,000 years. These moments demand a certain type of mind, one that is not so focused on the destination that it ignores the strange and wonderful scenery along the path. It's about embracing the detour, because in the labyrinth of the unknown, the detour might just be the main path in disguise. This humanizes the entire scientific endeavor, revealing it not as a cold, clinical process, but as a grand adventure driven by the same wonder that makes a child turn over a rock to see what's underneath. It's a powerful reminder that the next great discovery might not come from a multi-million-dollar machine, but from a curious person who simply pays attention to the world's subtle, surprising whispers. But this incredible journey of discovery, from the planet's churning core to its deepest caves, comes with a profound and non-negotiable responsibility. The pursuit of knowledge, especially in these pristine and fragile environments, cannot be a free-for-all. It must be guided by a strong ethical compass that balances our curiosity with a deep respect for the natural world and the human cultures connected to it. The first and most immediate principle is the concept of minimal impact. These underground labyrinths are not just geological formations. They are incredibly delicate ecosystems that have evolved in total isolation for millennia. A single misplaced step can crush a unique, slow-growing microbial mat that is the foundation of the cave's food web. The oils and dirt on a human hand can permanently stain a pristine formation, halting its growth and destroying its scientific value. Even the warmth of our bodies and the carbon dioxide from our breath can alter the delicate microclimate of a sealed chamber, potentially damaging formations that are still actively growing. This is why the caving community lives by the strict motto, "Take nothing but pictures, leave nothing but carefully placed footprints, kill nothing but time." Every action underground must be premeditated to ensure the cave is left exactly as it was found, preserving its mystery and its science for future generations. This duty of care extends far beyond the immediate physical environment to encompass the rich tapestry of human history and belief that is often intertwined with these landscapes. For countless indigenous cultures around the world, caves are not mere curiosities. They are sacred sites of immense spiritual significance. They are viewed as places of emergence where their ancestors first entered this world, as portals to the spirit realm, or as the dwelling places of powerful deities. In the American Southwest, many Pueblo peoples consider specific caves to be living entities, and their intricate oral histories often contain detailed knowledge of these spaces that has been passed down for thousands of years. For a research team to descend into such a place with drilling equipment and scientific instruments without prior, respectful consultation is not just ethically wrong, it is a profound act of cultural desecration. Ethical geological research demands that we engage with these communities as essential partners, not as obstacles. This means listening to their stories, understanding their protocols, and often integrating their deep, place-based knowledge into our scientific understanding. Their traditional wisdom can provide invaluable context, pointing researchers toward significant features or events that might otherwise be overlooked, transforming a one-sided extraction of data into a genuine collaboration that enriches everyone involved. The global community of cave scientists and explorers has recognized these responsibilities for decades, formalizing them into clear codes of conduct. The International Union of Speleology, the world's leading body on cave exploration, provides extensive guidelines that serve as a gold standard for responsible practice. These guidelines cover everything from the proper techniques for rigging ropes to avoid damaging rock surfaces, to protocols for decontaminating gear between caves to prevent the spread of deadly pathogens like white nose syndrome among bat populations. They emphasize the critical importance of obtaining all necessary permits, whether from government agencies or local communities, and of sharing the results of exploration openly and transparently with both the scientific community and the public. This last point is crucial. The knowledge gained from these hidden worlds is a treasure that belongs to all of humanity, not just to the team that collected the data. By publishing findings in accessible formats and contributing to open-source databases and maps, researchers ensure that their work advances our collective understanding of the planet, helping to inform conservation policies and inspire the next generation of stewards. This ethical framework transforms the adventurer into a guardian and the scientist into a humble student, ensuring that our quest to unravel the planet's deepest mysteries is conducted with the reverence, integrity, and care that such a grand pursuit truly deserves. So we've journeyed from the churning, liquid iron heart of our planet, out past the invisible shield it generates, and deep into the most hidden, beautiful caverns carved into the rock below. We've seen how the collapse of that magnetic field isn't just a celestial event, it's a planetary one, a cascade of chaos that might supercharge the very forces that sculpt our world. The evidence is compelling, written in the wandering poles locked in ancient lava, in the rapid growth rings of stalagmites, and in the very scale of labyrinths that defy simpler explanations. This isn't just a story about caves or magnetism. It's a revelation about the breathtaking interconnectedness of Earth itself, a system where an event in the core can whisper its effects through the climate, shake the crust, and ultimately leave a permanent, beautiful scar in the darkness. Understanding this deep, dynamic dialogue doesn't just satisfy our curiosity about the past. It equips us for the future, offering a profound lesson in planetary resilience and the complex, often unexpected, ways our world responds to change. It reminds us that the ground beneath our feet is not a static stage, but a living, breathing record of an epic history we are only just beginning to read. The great physicist James Clerk Maxwell once said that true understanding lies not in possessing a store of facts, but in fully grasping a handful of profound mysteries. The enigma of Earth's hidden labyrinths is one such mystery, a powerful reminder that our planet still holds vast, wonderful secrets waiting for the curious to uncover them. So keep that curiosity alive, look a little closer at the world around you, ask the big questions, and never stop exploring. If you enjoyed this deep dive into one of history's greatest puzzles, make sure to subscribe and join us for the next adventure. And we'd love to hear your thoughts down in the comments. What's the most fascinating mystery you've ever encountered? After all, the search for knowledge is the greatest labyrinth of all, and every new perspective helps us find our way through.